Okay. So you've done all this exponential growth decay stuff. It's just applications and reading the word problem, figuring out what to plug in where, and then solve it. So, numero uno. In 1970, the U.S. population was 203.3 million. By 2003, it had grown to 294 million. Use this information to write an exponential model. By which year, and then answer the question, by which year will the U.S. population reach 315 million? So, you've seen this formula. This is the PERT formula, essentially, that you did last year, PERT, right? But PERT seems to be used specifically with finance, but the idea of the initial amount, your irrational number E raised to the K, is kind of like your rate times T is your time equals your final amount. So what numbers would you plug in where? Give me one to start with. Jack. Equals what? For the capital A. Okay, so 315 is your A. Next, some other variable. Nathan Zorn. Debatable. It could be. It kind of depends. So if you decide that this is A sub 0, what would then be your other variables? So if that's A sub 0 and this is A, we have those two. What would be your K? Okay, because we would, if we did that, A sub 0 and A, we would still have two unknown variables. We don't know the rate and we don't know the time. So who can kind of wrap their head around what's going on here? Lily. Right, so there's kind of two different calculations that have to be made here. This will eventually be A on the second part of us doing it. Initially, though, because we don't have K or T for that final amount, we need to call this A and this A sub 0. Because for that transition from 203.3 million to 294 million, we do know the amount of time that's passed. It's not 3, it's... Did you say 33? I thought I heard you say 3. Yeah. So what did you see why it's 33? Yeah. So from that starting condition to that ending condition, our time has been 33 years. And so now we have enough information to find the rate of growth. So we'll plug in 294 equals 203.3. E to the K is what we're looking for, and T has been 33 years. So we're going to solve that, find K, and then readdress the question that they're actually asking. Okay, but in the meantime, we need K. So divide both sides by 203.3. This is definite calculator stuff. There will be 2 supplemental questions on your test on Monday that are calculator questions. 294 divided by 203.3 gives us kind of a crazy number. I can round when I'm writing it on my paper, but I'm going to keep that answer on my calculator. I'll just write down 1.446 equals e to the 33k. I do what to both sides, Michelle? Natural log, very good. So again, keeping that number stored on my calculator, I'm going to take the natural log of that previous answer. I get 0.369-ish equals 33k. and divide both sides by 33. So take that number as was exactly and divide it by 33, and I get k equals that. Okay, I'm going to round it to 0.011, and I'll use that and write that, but again, I'm going to keep that exact k value stored on my calculator. Do not hit clear. So now that I know k, I can now go back and answer this question. By which year will the U.S. population reach 315? So now that is the A value I'm looking to reach. Now here we have a decision. We can use a starting A sub 0 like we had before and use the 203.3. And so my T would be in years since 1970 if I use that one as my A sub 0. Okay? But you could also use this one as your A sub 0, and if you do that, then your T is going to be the number of years in reference to 2003. Does that make sense? So that's where Nathan and I was kind of getting at why you called that A sub 0. You can, but not until later in the problem. So I'm just going to stick with the original A sub 0 of 203.3. So my T value is going to be in reference to 1970. Then it's to the 0.011 power times T. So again, I'm going to start by dividing both sides by 203.3. So 315 divided by 203.3. Get that answer. It's 1.5-ish is all I'm going to write. I'm going to natural log both sides. So the natural log of that number gives me 0.438-ish. And then I divide both sides, not by 0.011, although in writing that's what I'm going to put. But what I really am dividing that number by, so divided by, I'm going to scroll back up on my calculator and grab that exactly. Do we follow? So as to not come across a rounding error. So I get 39. Say to the nearest year. By which year? 39.17. So by what year is that? I was going in reference to 1970. So 1970 plus 39.17 puts us somewhere in the middle of 2009 is when it's exactly going to hit that amount. So by what year? How would you answer that? Correct. That makes sense? Based on the way they phrased that? Because if you said it would happen by 2009, that's not true. It happens during 2009. So it's not happening by that cutoff. It's happening by 2010, which is one of those weird cases where you kind of round in the opposite direction that you would, and that's just the context of the way that that reads. Okay? Any questions on that? Go ahead, read through 2 and kind of set up what you're plugging in where, and then I'll check in with you. Say that one more time. E to the 47t? 0.5t? So you plugged in, the first thing that catches my eye is you plugged in the year 1946 for the starting value. That's okay. So tell me someone else where you started if you're feeling kind of confident. The rate of decay is the rate that it's decaying by on a yearly basis. So just because after 5,715 years you have half the amount does not mean, do you follow? Okay? This one's a little unique because they're not giving you a starting amount and an ending amount. This is half-life. They're just telling you that you have half the amount after 5,715 years. So to be honest, to start this problem, to figure out your K, you can come up with any starting and ending value pair that you want, so long as your end value is half of your starting value, right? So a number that I always find easy to do that with is make your starting value 100, and so half of that would easily be 50. And then e to the k, we're looking for k, but we know that that half-life happened after 5,715 years. Do we follow? So no matter what two numbers you picked, when everybody divides away their coefficient, they're going to get 0.5 on the left, no matter what, because you're making that ratio half to the other. So some people even do x, or 2x and x, or x and a half of x. When you divide that over, you're still going to get 0.5. Stephen? In this case, since my t is my number of years, yes, that's got to be in line with that. You wouldn't use years and then give me a monthly rate. Right. I know. That's what is confusing about it. But that's half-life is not the rate of decay is not 50% on the annual basis. Right. Right. You follow? Okay. So go ahead and find K. Natural log both sides. And divide by 5715. And I got a K equals negative 1.212855596 E negative 4. Do we all know what that means? Okay, so that's a very, very small rate of decay, which is typical for half-life, right? Because these things kind of decay in nature over 5,000 years, so that's to be expected. But now that we know K, we're going to use that information to answer the second question. In 1946, earthenware jars containing Dead Sea Scrolls were found, but that's fun history, but the math stuff comes in here. Analysis indicated that the scroll wrappings contained 76% of their original carbon. So again, you can make up a number. The starting amount could be 100, and if they contain 76%, what would your final amount be? 76. Does that make sense? I like to use 100 for all of these reasons. And then e to the k, we'll plug in our 1.2 kind of number, times 10 to the negative 4 times t. And we're going to find the age. You just don't want to write it. That's fine. So divide both sides by 100, you get that 0.76. E to your kt power, I'm going to take counters because natural log of both sides is going to give natural log, well, I'll just leave it like this. And then I'm going to divide both sides by that k number, which is on my calculator. So the natural log of 0.76 divided by, and I'm going to scroll up and I'm going to grab that K number. And I get 2,206. So say the nearest year, estimate the age. So estimate, round to the nearest whole number, 2,263 years old. Which is, I would assume, a pretty genuine way of finding out the age of fossils and bones and all that good stuff. Okay? So every kind of word problem you're going to read on tonight's homework is going to give you sort of details about what the variable stands for and so on. You don't have to memorize anything other than this, which is just the PERT formula. Something like this logistic growth model, it's going to give you an equation. So here's the generic equation for a logistic growth model, and we're going to talk about it in a second more in detail once we wrap our head around the context. This function here describes the number of people, so f of t is the number of people who have become ill with the flu t weeks after its initial outbreak in a town with 30,000 residents. And that is where the 30,000 in the numerator has come from. Part A says, how many people became ill with the flu when the epidemic began? What would you plug in for what if you were trying to answer that question? T is 0. Very good. So you would just do f of 0, the number of people at the 0 week mark, is 30,000 over 1 plus 20e to the negative 1.5 times 0. And just plump that into your calculator. Make sure you keep your denominator in parentheses if you're not using the so 1,429 approximately. It's people, so I am going to round to the nearest whole number. So in that start of this, 1,429 of the 30,000 got it. Part B, how many people were ill by the end of the 4th week? We're just going to do f of 4, so same thing. Do you all know how to kind of redo it without retyping everything in? Scroll up, grab that, it's going to bring it down, and I'm going to go into my equation and change my 0 years to 4 years and just hit enter. 28,583. And then C is, what is the limiting size of this? What is the limiting size? So meaning, as our number of weeks approaches infinity, right? So as t approaches infinity. So maybe just plug in something absurdly large, like f of 100, 100 weeks. That'd be almost 2 years after the fact. So if I do that and plug in 100 for my number of weeks, any ideas? Yeah, 30,000. Why does it make sense that... Wait, what, Adam? Right, exactly. You only have 30,000 people in the town, so it can only affect 30,000 people. So if I were to graph this function, what would you expect to see? A horizontal asymptote guiding your behavior towards infinity, capping things out at 30,000. Nice. It's not. It's not. It's actually going to be 29,000.99999999999. Your calculator, though, only has so big of a screen as well. So it actually never reaches the 30,000. Now, logically, everyone could be affected by it. So we know that it could, but that's kind of the best model for something like that, because think about this graph. It's going to shoot up quickly, and then it's going to even out, right? That's what happens with sicknesses as they spread. It spreads really quickly, but then once most people have gotten it, it kind of balances out. Right, Liz? Who's going to infect us all today? All right. New one's all cooling. You did this last year. This formula might look a little bit different, but again, it's going to give us the same information, maybe just using different variables. So a cake removed from the oven has a temperature of 210. What variable do you think that goes in for? T sub 0. That's the initial temperature. Good. It is left to cool in a room that has a temperature of 70. Do you know where 70 goes? C. Correct. That's the room temperature. C is room temperature. So that's your C. After 30 minutes, where's that going to go? Lowercase t stands for time. The temperature of the cake is 140. Where's that going to go? Big T. That's your final temperature. You got your starting temperature, T sub 0, and your final temperature, T, 140. What is the temperature of the cake after 40 minutes? Okay, so they're asking us for something that we can't know until we find K, which seems to be a common theme here, right? So given the information they've currently given us, we're just going to pause here, look for K, because once you find K, just like variation problems, that K remains constant throughout the problem. So go ahead and do that. A lot of number crunching here. Oh, I have a common mistake I can now remember people making last year. 210 minus 70 is 40. 140. I remember a lot of people making this 210. Don't do that. Okay, that's not 210 ek to the 30. If it was 70 ek to the 30 plus 140 ek to the 30, then you could combine them. They would be like terms. They are not like terms. This is a constant that needs to be subtracted first. I know that seems silly to some of you. You would never dream of doing that, but there are definitely people who would do that. Then you divide by 140. Natural log of both sides, so the natural log of 0.5 is negative 0.693-ish. Equals 30k, divide by 30, k equals negative 0.023-ish. I'm going to keep the exact answer on my calculator. Now let's answer the question. What is the temperature of the cake? So what is the final temperature of the cake after 40 minutes? So it's, what do you expect it to be? If after 30 minutes it's 140, after 40 minutes you expect it to be higher or lower than that? Lower, because we're cooling off. So always have your kind of finger on the pulse of what is going to be an appropriate answer. In the event that you get something that's way off, you'll know you did something wrong. So T equals, your C is not changing, your initial temperature is not changing, your K is now at negative 0.023 number, and we're solving for T. Oh, no, we're not. T is 40. So this one's nice because the variable we're solving for is already by itself. We can just number crunch. Type this exactly as you see it into your calculator. And what did you get, Liam? Which is lower than 140 like we thought. Okay? I think a little bit more challenging than what you did last year, just because there's like these two steps, like use your given information to find your constant, and then use your constant to answer a follow-up question. Is that fair to say? Okay. Let's jump to 6. I almost have to remember this. We have seen that the function here models world population Y in billions X years after 1949. Rewrite the model in terms of base E. Oh, I can't remember what they wanted us to do here. You're going to see this on your homework, so I got to look this up quickly, because I forgot. Page 433. Oh, yeah. So they slip in here in order to write it in terms of base E, so it's going to be more like the PERT formula. They slip in here 2.557 e to the natural log of 1.017 times x. What's that? Well, because right here you can't, it's not in that PERT formula. So in an effort to find out what that k value is, do you see how that's an equivalent expression here? Because e to the ln would just cancel going the backwards way. You see it? Well, no, they'll tell you kind of to rewrite it in terms of base E. So this kind of E ln on the reverse would cancel, and then it would just be 1.017 to the x power. So it's kind of going backwards and inserting it versus canceling it. And then when you figure out the natural log of 1.017, you're going to actually calculate this on your calculator. So it's 2.557 e to the 0.016857-ish x. So the k value is close to 17, I guess 1.7%. It's 1.6857. Did you guys ever think that last year, like, and you probably drew the connection from a different vantage point, but that is a 1.7% rate of increase, we would say, right? Because it's 1 plus r. Do you remember that? When it equates to the PERT formula, it's close. That rate from the PERT formula is close, but it's not an exact replica of the rate that you see when you think of this as 1 plus r, just for the record, okay? Dave. I'm not canceling them. I actually inserted it so that I could convert this to the PERT formula. Do you follow? I was trying to make people see that kind of working backwards, if you did cancel it, that's an equivalent. But they insert it purposefully so that it molds to that PERT format. And really quickly on 5, I'm not going to do it, but when you get to this on your homework, write an appropriate function. You're going to have to enter this data in and run a scatter plot on your calculator. Oh, look at it. So enter the data and then run a regression to get a function, a best fit function. You know what I'll do on that?